welcome everyone. I hope lunch is already a little bit digested because I have a lot of information for 1 hour and I will try to ram it all in. So be attentive and it's going to be a wild ride. Basically, the idea of this talk is to give you some insights in a service that we've had running in JetBrains for a long time, but that is legacy, as we call it. It's the thing that works and the thing that generates money and so on, but it's legacy. So we wanted to think of what would be a nice architecture to come up with a better approach to build that thing, and that's what this talk is about. So I don't know if anyone here is using Resharper or Rider. Okay, thank you again. In there is a feature called Find This Type on NuGet. Basically, when you write your own code, you will see that when you start using an object type, like for example, JSON convert or JObject or whatever, there will be a quick fix available where you can search that type on NuGet, and Resharper will come up with, okay, this is newtonsoft.json, install this package, and you can start working with this type inside of your application. Works with types, works with namespaces, and so on. That thing was introduced in Resharper 9, I think, in 2015. The idea actually comes from 2013. That was when I just joined JetBrains. We had a company party in Finland, I think, even. And I was talking with some guy and saying, look, this would be an awesome idea. I was 2 weeks in JetBrains, so I thought, okay, let's give these guys some hints and become more awesome. And he told me, yeah, we're working on that for ages now, so that's coming anyway. So I didn't have a very novel idea, but again, it's been there for a while. That service or that feature in Resharper contains or consists of a couple of things that are needed. First of all, Resharper itself and the quick fix that is in Resharper, so all of the functionality that you get in your IDE, but also a service that indexes the packages that appear on NuGet, cracks them open, looks inside and sees what the public types and public namespaces are, and then puts that in an index so we can search for that thing. Now, back then, this was built as an Azure cloud service. Anyone still using those? Am I really the only one? Yes, more people like me, thank you. That works perfectly, still works perfectly till today, but you can feel like there's not a lot of attention from Microsoft in the cloud services space. So it looks like they may be going away, or I don't know, but it doesn't get a lot of attention. So it kind of means something's fishy there. That service is a web role, which provides the API towards Resharper so that we can use the functionality from an API. And we have a worker role doing the indexing, so fetching packages from NuGet and so on. Now that indexer, till today, still uses the NuGet OData feeds. Anyone ever tried OData? Like the XML version of GraphQL back in the days? That thing was perfect for NuGet, except that that thing also was a little bit of a HTTP interface towards a database. So if you look at the query that we do, for example, what we try to do is fetch for every single package in there. We fetch ID, version, normalized version, last edited, and so on. And we filter that by last edited is greater than a specific date that we get from there. What you get back is OData, and you see I have an XML extension, so that means my life consists of XML. You will see that the packages are listed there. We get an entry. Each entry has the author information, a link to the actual package, and so on. And somewhere at the bottom of this page, you will find a link to the next page of results. The way OData works is that it's a feed, much like an RSS feed, that you hit, and you get pages to the next page and so on. So we started to see a couple of things building this crawler and this indexer, in that fetching all those pages was starting to get slow. Because the way NuGet works is they have a search engine for typical searches that you do in Visual Studio or VS Code or whatever. But they also have an API where you can get all of this metadata, and that is literally OData on top of Entity Framework hitting their database directly, and that database doesn't like us doing a lot of things that we do. Also, NuGet over time has been growing quite a bit. This is, by the way, the guy that I talked to in 2013 who built that feature initially. When he logged onto that cloud service and looked at the disk, he saw that we had close to 1 terabyte of packages cached on disk there, which was interesting. Well, close to 2 terabytes actually. So over a couple of years, NuGet has grown quite substantially. And yes, we cache every NuGet package on that system, because if we have to do a reindex, we don't want to go and download everything again from NuGet.org. so that we don't have to bother them with things that they don't care about for us. NuGet over time also introduced a couple of new features. Anyone heard of repository signing? Basically what you can do is when you have a NuGet package, NuGet.org will sign that package to prove that the package you're installing actually comes from NuGet.org. Now, that was a feature that was only introduced somewhere last year in August. And we saw in our indexing process that they started doing this signature, started applying those signatures around Christmas and New Year last year. So end of year, beginning of this year, where they were doing this. Why did we notice this? Because our queue of packages to index was growing tremendously. Because every single package binary that they had on NuGet since the beginning of NuGet, which is 2012, I think, every one of those package binaries was being signed, so the binary changed. All of the last updated dates were updated, so we had to basically re-index everything that was coming from NuGet. And that was a lot of work for our search engine. We also found that fetching all of those pages with all of those changes was really getting slow over OData. First couple of pages are still quite fast, but the further you go in that result sets, the slower it goes because you hit the database has to skip and take a number of results and so on. So we saw that that was getting slower. Now, if you have looked into NuGet or not, I will tell you a bit of how their API works. So the V2 API, and actually version 1 as well, was an OData feed. The current one that you're using in the later versions of Visual Studio and so on is the V3 API, which is JSON-based. There's a couple of third-party vendors like MyGet, like TeamCity, like NuGet itself, also offering those feeds, but most actually have that OData feed available. Now, the V3 feed, in terms of functionality towards really installing packages in your application, I don't think it gives a lot of value except that it's JSON and it's not hitting the database directly, but other than that, there's no real benefit there. What is interesting though is that the V3 API is actually some kind of a protocol. It's a resource provider. The moment you enter the API URL in your browser, you will see a list of resources that you can hit. Pretty much every single use case in NuGet today has its own API. If you do a search, you hit the Search API from the V3 protocol. If you do a package restore, you hit some blobs that have a template. If you download a package that is not in a restore but an install or an update, you hit another one, etc. So you will find in this index.json, you will find a lot of things like a catalog, registrations, a flat container resource, even the URL where you can report when a package is broken or something is in that protocol. So if you go to that page, you will see a lot of things that don't really mean a lot at first sight. So if you look at the API, all that you will see is that we have this URL, and I clicked it, this URL that will do search because it's a search query service. There's a couple of those in US North Central, South Central apparently. There's an auto-completion service for when you're editing the project file directly, so you get auto-completion and so on. The galleries there, registrations are there. I'll cover those in a bit. The old API is listed in there, so lots of resources that you can hit for certain use cases that you may want to do. Now, how does NuGet work when you upload a package to NuGet? Apparently, this is no longer completely true since Monday, I think, because they changed the way a lot of things work. But generally, this still holds kind of true. When you upload a package to NuGet, what happens is your package is stored in the database, the blob is stored somewhere on storage so people can restore it and so on. And then various jobs run over a catalog. That catalog is a representation of what is in the database at any given point in time. So basically they have an append-only structure that holds all packages since the beginning of time with whether they were updated, whether they were deleted with newer versions, author updates, etc., etc. Various jobs run over that catalog, so they populate the index based on that append-only stream, because you can have a cursor, read from that append-only stream and get all that data and add it into search. So we thought, okay, that catalog may actually be very interesting because it's chronological. You can use that cursor and actually get data for a specific time range and so on. So let's dive in and see what it does. So By the way, I'm covering these things because they will matter when we start doing Azure Functions and the stuff that we will be building. So if we go back to the NuGet API, at some point you will see that there is a catalog. And that catalog is some index.json that you can open. And what you will see is more JSON. And all of the JSON you will see here, when it renders eventually, yes, there's a lot of data, is a number of pages. And every catalog page has a commit ID and a commit timestamp. So basically, if I would be interested in all of the packages between last week and this week, I could read this file, look at those timestamps, and get only those pages that I would be interested in for that time range. When I look into one of those pages, you will see that there's catalog leaves in there. So every page has a count. There's this many packages in that page, and you will see all the items there as well. Not a lot of details, basically just the ID and the version, and also, again, the timestamp. So if I want to do more fine-grained checking of which packages were added or updated or deleted, I can use that timestamp there. Then every package also has an ID. And if I follow that one, I actually get the details of that package. So NuGet does a lot of the opening up packages and fetching that metadata for us. In this catalog, we can see who the authors of a package are, what the description is, where the icon URL is, what the package hashes, etc. So there's a lot of information in there, and we can actually flow through that entire catalog and fetch all of the data that is in there, or maybe in there, which is what you can do in code as well. So if you search on NuGet itself, you will find a package called nuget.protocol.catalog. I didn't add it as a package reference here. I actually used the codes in this one because I wanted to make a couple of small changes in there. But generally speaking, you can fetch this from NuGet and look at that catalog yourself if you want. The way this thing works is that if I want to dump everything that comes from that catalog, what I can do is create a batch catalog processor, which is something that comes from that package. I give that processor an HTTP client as well as a cursor. So if I want to say, for example, that I want all of the packages starting from date time offsets .utc now.add hours -1. If I want to get the packages from the last hour, I can set this cursor, and that batch catalog processor from this package will start fetching everything from that point in time. Then I have some other infrastructure that is needed for that thing to work. And then I have a catalog leaf processor. For every single package that appears in this catalog, I either get a callback to my added lambda here, so I can parse my package version, print something like this package was added to the console. And when a package was deleted, I can do the same thing. Notice there is no update here. Whenever an update to a package happens, which in theory shouldn't happen, but in practice does happen quite often, it also goes through this added function. So there's no real distinguishing between added and deleted. Now, if I want to run this, I can do so and say, okay, run my catalog dumper, and this will fetch the catalog and give us live the packages from the last hour on nuget.org. I hope some people submitted some packages. Apparently they did. And we can see that, for example, test lab standard version 1.0 was added to the catalog in the last hour. You didn't know this, now you know. You're welcome. Right. So back to our fine type on nuget.org. We thought, okay, if we have to refactor from OData to v3, that's a lot of changes in our current code base, so maybe we can start building a new version. We started doing that, actually a couple more versions than the one that I will be showing in this talk. But we also did update the old version just in case we didn't come up with anything new. So the old version can now also use v3. And that is about to go to production with one minor blocking issue that we still have, which is that NuGet doesn't expose download counts. And if you want to make a search engine, download counts are a pretty good metric to determine whether a package should be ranked higher or lower in search results. So that's a bit of a downside right now. Right, so let's build a new version. What do we need? We will need something that watches this nuget.org catalog and checks for changes. For every change, we will have to download the package, crack it open, scan the assemblies that are in there, see what public types and public namespaces are in there, and store somewhere in a data store the relation between package ID and package version plus those public types that are in that NuGet package. Once we have those, we also would like to have an API that is compatible with every Resharper version out there, so that when we switch the URL, people can just continue using it without having to have client-side updates in the products. So bonus points would be if we could re-index quickly. If all of a sudden NuGet retracts package signing or something big happens and everything has to be re-indexed again, it would be nice if we could do this as fast as possible and not have to re-download everything and go slow over that entire catalog. So watching NuGet is kind of something that we could do based on a timer. Every 5 minutes, every minute, every 10 minutes, maybe every hour, check whatever changed on there. Then push all of that stuff into a queue, and then for every item in that queue, which is a package addition or package deletion, do all those things. The API, we could use pretty much anything that exposes an API, so an app service, maybe an HTTP trigger on Azure Functions, doesn't really matter, just an API. This kind of sounds like a nice scenario to use Azure Functions for, right? Because in Azure Functions, you have inputs, then some code runs, and then you have outputs. Now everyone is an expert in Azure Functions. This is official documentation, by the way. And yes, I too find that very laughable, but there's a very, very good thing hidden in this diagram, which is additional text. The additional text gives you information on why this workflow is important. Basically, what the text below says is that your code will run based on an input coming in. So whenever something happens, you get a function that executes. You actually get a reactive programming model based on events that happen in pretty much anywhere you want. You run some code, you provide some output. That output in itself can then again be an input to another function, and you can have another event running whatever code you want to run in there. So it's actually, it sounds ridiculous to only have input processing output like the old diagrams from the 70s, but there's a good core of truth there, and your functions will even scale based on the input coming in and yeah, how fast you want to process all that input. Right, so for our solution, we thought, okay, let's break down this problem. And what we want to have is a function that watches the catalog. We want to have a function that then checks the queues that are populated by that first function, want to index the package and want to download the package. Again, we wanted to be able to quickly re-index packages. So what we want to do is also download them for further use so we can re-index them if needed. Then we index everything, store it as a JSON, push it into search, and then we have two functions for the actual search inside of the products. So let's go through them. So collecting from the catalog, we could do that using a timer function. So for example, what we could do is create a new HTTP trigger. Let's call it Foo because we're at Foo Café. There we go. Add it to Git, all fine. And then we say, okay, we get, that's an HTTP trigger. I needed a timer trigger, of course. So let's say we want a timer trigger. Let's call it Foo again. Yes, add it. It runs every second, I think this is. Yes, and we get back a timer. Now, the nice thing about having a timer for this function is that we can write our code using that timer. This timer has a schedule, so I know when it will run next, but I also get from that schedule when the previous occurrence was. So given the fact that our catalog has timestamps as the cursor, I can use this timer to determine the window for which I want to fetch the data from that catalog. So I can use whatever is in there. So I'll quickly use a snippet here and complete the code like this. There we go. This is how everyone writes code, right? And make that an async task. There we go. So now we have a function that pretty much does exactly what we had in our console application previously, only this time it will run based on a timer trigger. It will process our catalog based on the last timestamp from my timer and until now. So the next time this runs, I will get a new window. So instead of fetching everything that is in there, I only get since the last occurrence of my timer, right? So if I would run this function, and I can say, okay, only run this function, we will see at some point, yeah, fine, functions host can run. We will see at some point that my function will be triggered and data will start coming in. Now this may take a while because first of all, I think I made it only every minute, my timer function. So we may have to wait for this to happen, but trust me, you will see exactly the same as before. And again, this package, I don't even recall the name what it was, but this package will show up in there from the last hour. Right, let's skip that one. So essentially same code that we had previously, but now we're already serverless. We have a function triggered by a timer and that runs whatever we have in there. Cool. So that's done, right? Well, no. We started reading about functions as well. And I don't know if anyone follows Paul D. Johnston. He's basically the one that started building Lambda at Amazon. And he has a lot of best practices that apply in microservices and functions, whether that's on Azure, whether that's OpenFaaS, whether that's AWS Lambdas. He doesn't care. He has lots of good practices. One of those best practices is that each function should do only one thing and only one thing well. Sounds a bit like regular software development, but there's a good reason for this in the context of functions. It makes it easier to handle errors. It makes it easier to scale your function, and also troubleshooting becomes much easier because you know that function only has a couple of lines of code, so you know where to go and look for whatever you have in there. A sort of consequence of having each function do only one thing is that you need a way for those functions to communicate with one another. And typically you will land on something that is a message-based approach where you put messages in a queue, process those messages, and so on. So right, let's collect from our catalog using a better version. So instead of having the responsibility of triggering on a timer, then setting up all this, and then doing all this, this stuff that we have here, let's see if we can reduce the amount of code that is needed to do something here. So what I have here is exactly the same code, but instead of processing it inside of my delegates that I have here, what I will do is add my packages to a queue collector. So in my function here, I have a parameter or an argument that is called queue collector. It's decorated with a queue attribute there, which basically tells the function's runtime, okay, whenever you see a message appear on this queue, push it into this queue collector, or in this case, since I use it as an output, whenever something is added to that iCollector interface, push it onto that queue. So that's what this function is going to do. Still the same code. Check my catalog. Whenever a package is added, push some message onto a queue for further processing. So that's what we're doing here. My indexer itself is still very, very simple, although here we trigger based on a queue and we simply log the fact that the package was added. So if I would run this, you would see, again, exactly the same thing, but I already broke up the problem into two functions where one fetches stuff from the catalog and adds it into a queue, and then I have another one that runs based on that queue. Already, you can see that I could have one of those collectors go over the catalog and fetch the messages from there. But then this one that will do the actual indexing, I could scale up to 1,000 of these, and they will all just check that queue and check what is in there and do whatever they have to do with that message in that queue. So we already split a couple of things there. Now, I use that queue binding because bindings are a very important concept in functions. You may have seen, has anyone actually tried functions? Okay, most of you good. You will see that most of those bindings are available out of the box. There's a timer binding, which will trigger your function executing. There are HTTP bindings. Basically, when an HTTP message comes in from the internet, your function will run. There's blob bindings. When a file appears in blob storage, the function will run, etc. Some will trigger your function to run. Some will provide input to your function, and some will provide output or read output from your function and process it somewhere. There's a couple of them out of the box for HTTP, blobs, queues, service bus, event grid, whatever you want to do there. But you can also build your own. I have seen on the internet SQL Server bindings. Basically, I think it was Christian Weyer, if you know him. He has a timer-based function, so it triggers based on a timer. He then uses a SQL Server binding to get input from a database and then process that in that function. Same with output, you can create your own output bindings. Now, one binding I kind of miss here is a NuGet catalog processor binding or something like that, whatever you want to call it. So we should write that ourselves if we want to do this. Whenever a new message appears or whenever a new entry appears in the catalog, I want my function to trigger and get that data from the catalog. Now, custom trigger bindings are not officially supported yet. The yet, I hope it comes at some point, but they are not officially supported. However, we've been using them for 3 months in production now, and we only have seen them fail twice, I think. So if you have monitoring, they're pretty stable if you use them. One place where you cannot use custom trigger bindings is in the consumption plan in Azure Functions, because that thing shuts down after a while. But as long as you have reserved capacity and you basically have your own server running your serverless stuff, you can run it there and it will work perfectly. So let's build our own NuGet catalog binding. Right. So instead of having all of this clutter checking the catalog, I want to extract that into a trigger binding so that my function triggers and I can simply put something into a queue. So basically what I want to end up with is something like this, where I say I bind to a NuGet catalog trigger. That thing gives me a package operation, and then I can simply forward it onto a queue for further processing. Now you might think, why am I using that queue again here if I already have that binding and I could process it immediately? The problem is, if something fails, the catalog binding will stop. My catalog binding is also only one thing following this cursor over the catalog, so it's very difficult to fan that work out. So basically what I want to do is fetch everything that I have in there, push it onto a queue, and then fan out that queue for further processing later on. Right, now how does that catalog trigger binding work? If you look at bindings, you will see that they are pretty simple. They're just an attribute that has properties that you can provide defaults for, that you can use for configuring that binding, etc. So what our binding will need is the URL to the NuGet.org API. It will need to know the previous hours to process. I added this for debugging so that when I pass it a 1, it will fetch only the packages from the last hour, for example. What I will also need is a connection to storage, a name of a cursor container, and a name of a cursor blob name. So what I want to do is, I think I removed it. What I want to do is keep track of where I am in processing this NuGet catalog. So I will need to persist somewhere what the timestamp is that I last processed over that entire catalog. So that's what I want to store with these values. Right. What's important if you want to declare your function, your own custom binding, is that you annotate it with a binding attribute. I have no idea what it does, because if you add it, it doesn't work because you have additional work to do. If you don't add it, things will fail, so add it, but I have no idea what they use it for internally. The next thing you will need, and let me go there. The next thing you will need is an extension. Basically, you are extending the functionality of the Azure Functions host, which means you have to register your custom binding as an extension to that functions host that exists. And we can do that in here. What we say is we have a, sorry, it's this one, right? No, it's, yeah, no, it's this one, sorry. So what we have to do is create a class that implements iExtension config add an extension attribute on that one, and then use that to register the custom binding that we have. So what we say is, for all of the extensions in the functions host, I want you to add a binding rule based on the attribute we just created. So whenever you see this attribute, bind it to a trigger. And that trigger is going to be my trigger binding provider that I have in here, which I'll cover later. Now, if you read the documentation, this is all they say you have to do, create that binding attribute and then add this extension one. There's actually one more that you have to do, which is create a startup class, add a web job startup attribute at the assembly level then, and then configure that thing much like ASP.NET MVC and ASP.NET Web API. So basically say, okay, I'm adding my catalog trigger binding provider in there, registering it in functions. Now let's dive into the meat. There's a lot of code for something fairly simple, but it makes our code very pretty, so it's worth going through that. Right, so we configured our thing, and we configured this binding to use a NuGet catalog trigger attribute binding provider. Very long name, but also very important. Even though you register some things internally, the functions runtime expects type names to be what they are. So if you say I have a NuGet catalog binding, if you create a trigger binding, you will be expected to add a trigger extensions config provider and all those other types as well. So don't choose a long name for your binding because you will end up with large class names there as well. Right, so what this thing will do is basically get things set up. When it encounters these attributes, it will create a storage account that I want to store my cursor in, and maybe set up logging and so on. So what I'm doing here is when try create async there is called, I want to check what the attribute is. If there is an attribute, I will check if I actually support the type that is being requested, because I cannot support every single type with that NuGet binding. There's only one shape of objects that you will get from there. And once I have that, I will set up the account, create a blob client, create that cursor blob, and be able to store that thing. And then create a NuGet catalog trigger binding. Again, kind of by convention and kind of by name. So my NuGet catalog trigger needs a NuGet catalog trigger binding type to also exist. This one will do some more setup work. It will basically provide the translation between what comes in and what goes out. So you had the input, processing, output. This one formats the input, and if you have an output binding, it will format the output of what you will be storing in AQ or wherever you want to store this thing. So what we do when we create this listener is lots of things, but what I want to focus on is that there's a binding data contract that you can specify. You don't have to do this. The only thing you have to do is provide this data object and then say some JSON can be passed around. But if you want to be friendly to other runtimes or other languages in your functions host, you will have to provide all of these other things and say, okay, I have a property called ID, which is type string. I have an isListed property that is a Boolean, an action that is a string, and so on. If you're building functions using Python or Node.js or whatever language you want to use on functions, if you don't add these to your custom binding, you cannot really use that custom binding in those languages. By adding these things, you're kind of preparing the schema for those languages to also be able to work with the custom binding you're creating. So you can create this trigger binding in C# and maybe write the logic in Node.js or whatever. I have my binding data contract, but of course I also have to be able to bind my data. So what I will expose from my trigger binding here is an object, and an object is only that. So I also want to add all of the different properties that I have there and provide that binding data to the function's runtime. So that's all what is happening here. Again, not going to go into all of the details of this thing, but just so you know, if you provide this thing, you can also support all of the other languages in functions. Right, the next one, a to-do. This is also a nice one. If you overwrite this one, which is why the to-do is there, you can also influence how the function output will be logged in the portal in Azure. So if you want to have a fancy debug string there, you can add it here and expose that through the portal as well. But apparently I forgot. Amazing. Next thing we have to do is build the actual trigger. So far we registered the thing. We specified that we have a custom trigger. We specified what the shape of the data looks like. We have our storage account set up to store that cursor towards the NuGet API. The next thing we need is the actual listener. So what we will do is create that catalog listener based on whatever arguments that I pass into it using my custom binding. Then set up the exact same thing that I had before, my batch catalog processor that in this case not uses a timestamp to get the data, but instead uses a timestamp that is backed by blob storage. And then either run the package added or package deleted methods whenever a package is added or deleted. This thing should be able to be started and should be able to be stopped. So if you create your own trigger binding, the runtime will call start async whenever it's ready to start processing. Whenever the function's host is shutting down, it will call the stop async. You can do a couple of things there, maybe store some state information or whatever you want to do based on the use case you have. In my case, I had no use case, so I said, okay, task.completed task. Right. The only thing that's really interesting here is when a package is deleted or a package is added. What I get from the function's runtime is an executor. I think it's called, it's an iTriggered function executor type. that executor is basically where I tell in my binding, hey, functions runtime, here's some data to process, maybe call that function that you annotated this specific function with. So what I say is when a package is deleted or when a package is added, hey, executor, try executing this function with triggered function data where I provide my entire package operation, which can be an add or can be a delete with all the details that I want to pass in, and then pass that along to my function that I have, right? This will trigger the actual function. So if I don't do this, my binding will still run, but function execution will not happen. What is behind that executor? I have no idea, although I actually have an idea. The runtime, what it does is use an internal queue to process whatever you pass in there and then call the function that you want to call. So it's not that you're calling the function directly here. If you call this executor.tryExecute async, you're basically telling the runtime, hey, please run this function with this data. So that's our custom trigger binding. And if we have that, we can simply run that one, and we should be able to get the data that we have using our custom binding. So if this one runs, we should again see data coming in, or at least we should see things being queued into a queue. Generating 11 job functions. My project is too large. Taking a long time. Maybe let's not wait for it because it's a dull demo. It just outputs again packages to the console there. Right, let's close this one. So anyway, in summary, what we have now is a very nice approach to our indexing. We now have our enqueuer, which uses the NuGet catalog trigger binding that we just created. Whenever a new package appears, the function executes. We have two queues, our indexing queue and our downloading queue that we populate in there. So we get the data in, our package operation from the custom binding that we just created, add it into two queues. And because I mentioned we want to be able to reindex packages fast, I'm kind of committing a sin towards that principle of only doing one thing in your function. We're also storing the package entity in table storage just in case we need that metadata later on. But in general, we're just pushing stuff into a queue. Okay, we're making progress. We already have the first one down and we're far beyond halfway of the session. We have the catalog. We're watching the catalog with a custom trigger binding. So all of the things our code is still doing is getting data from that custom trigger, the input part, processing it, adding it to a queue collector, and then providing the output into a queue for further processing. Now let's look at indexing package. Actually, let's look at downloading packages first because that's going to be much simpler, right? Downloading packages is something that we can do using a very simple function that again is triggered based on a queue. Whenever it sees a message appear in the downloading queue, we will start downloading a package. This code is definitely not rocket science because the message I get back from that queue is going to be a package operation. When it's an add, I will run this code. And what that code will do is fetch a stream remotely, fetch the package from NuGet, and upload the package to a package blob that I have. So this is really, again, input-output. I have input coming in from a queue, processing it, which is the actual download, and then uploading it into blob storage. Now note, I'm making use of that blob that I'm uploading to, but I'm also making use of the output binding for this blob. So I'm asking the runtime to give me a reference to a blob in blob storage so that I don't have to spin up a storage client, create a container, do all of that work in my function. No, I simply tell the runtime, give me a blob that I can write to in this specific container with this format of name. Speaking of that format, the blob output binding is kind of interesting because you can also add parameters in there. So if you say my blob name should be packages/package ID/package version and so on, what I can simply do is make use of the properties that come into my function, and the blob trigger binding will automatically map these into the file name that you want to store on blob storage there. So that's pretty much all it's doing. I will give you one additional hint here. In my function, I make use of a static HTTP client. If you use dependency injection, you can make use of the HTTP client factory, etc. But the thing is, if you would run this downloads function highly distributed on one server in Azure. That server will probably exhaust its TCP ports because you're newing up a new HTTP client every single time. And that's why I'm sharing that so that it can share the connections and not get that effect of basically killing the VM running the functions. So keep that in mind. If you have to do some HTTP work, use the HTTP client factory or use a static HTTP client so that your function will essentially keep running. Right, that's the download part. So let's go on to the next one. We have downloading now. Let's start indexing the packages that we have. Now to index the packages, there's a couple of things we have to do. We have to open up the NuGet package. A NuGet package, by the way, is just a simple zip file and there's assemblies in there. Open up those assemblies, see what public types are in there, and then push them into an index that we may have. Now, how you can approach this is by opening up a package, checking all the assemblies that are in there, and reflection, assembly, loading, whatever, those things into your process space. That's probably not a good idea. Imagine indexing a couple of million NuGet packages and loading all of those assemblies into your process. I don't think you want to have that. One, it will be slow. It's a big security issue. And yeah, there's lots of downsides there. Luckily for us, there's a package called system.reflection.metadata that gives you access to the data structures that are in an assembly. And those data structures inside an assembly give us type names, give us type information. Is it a public or a private type, and so on. So we can use that package. So we will use that package to crack open whatever is in the assembly, and then we will store the package ID version plus the public types that we have in Azure Search later on. Now, for those who don't know, and I hope you don't, there's not a lot of people that know how this works. If you look at any .NET assembly, there's a header in that assembly file. Basically a set of tables containing information about whatever is in there. And one of the tables that you will find in there is called type def, the type definitions of things that are in that assembly. And if you go through there, you will see pointers towards a type definition, but you will also see a pointer towards the name of the type and whether that type is public, private, and so on. So you see that this one is called bearer token connection, the type name for type number 1 in my assembly. That name actually comes from another table called strings. So basically the name and the namespace are again pointers to another table that give me back the actual name of that function. I wanted to visualize this because the next thing we will do is make use of this in code as well. So I have it on slides because I wanted to add animation, but essentially in code it will be the same. You will see that we create a new portable executable reader that comes from this package. We open up the metadata stream that is in that assembly that we are opening, and then we check every single type definition in the type definitions table. For every single type definition, we will check, is it a public type, yes or no? If it's not a public type, we're not interested, continue. If it is a public type, we want to follow the string references to the namespace name and the name, so we do that. And we also want to do some filtering as well because there's generated classes, there's things generated by the compiler in every single assembly that are public, but I don't think anyone will ever want to search for C__display class when they're writing code. At least I really hope you're not wanting to do that. Right, next thing we need when we have that data is pushing everything into Azure Search. Azure Search is search as a service. Basically, I think it's backed by Elasticsearch or something similar. It's a service that you push data in. It will index it based on the shape of the documents and the fields that you put in there. So basically what you have is the service. Every service will contain one or more indexes, and those indexes will contain documents, and every document will consist of fields. So it's literally a tree of a couple of things and some metadata on whether a field should be indexable, should be searchable, and so on. So we will have to define what that shape looks like, and then simply store it into Azure Search so we can do the actual searching later on. So let's index packages. 15 minutes left. I better be quick. We have our package indexer. And again, that indexer, what it will do is make use of a queue trigger. We already had our custom binding pushing stuff into a queue, and then we have that queue to fan out the actual indexing. So we read from the queue to start indexing. Once we have that, we can create a new search service client, which is the client API towards the search service on Azure. and then run an add or a delete operation. Right, let's first go into the indexing part for a little bit. The index that we have will consist of documents called package document. Package document is not something that Microsoft gives us, it's something that we have to generate, but it specifies the shape of the data that we want to index in Azure Search. So what we have is a package document. Every package document will contain lots and lots of properties, and for every property we have to set what we want to be able to do with that property. So for example, we want to have an identifier. Why do we want to have an identifier? So we can search a document in that search index by ID, and whenever a package has to be deleted, we can delete it using that key, right? We also want to have the package ID and the package version in there, because of course that's what we will need in the API later on. And we want the package ID and the package version to be searchable, so that when we search for a package ID, we could still find it. We want to make it sortable as well, so we can sort packages based on whatever property we have there. And we also want to make these retrievable, because if you look at the way Resharper does it, if you use the API here, we get a nice listing of the actual package, a nice icon, and so on. So you want to be able to return that data as well. So by default, if you only make your properties searchable, you will not be able to retrieve the original data. You will be able to search for it, but you will never see what was in there in the first place. So you have to be explicit and say, okay, this is also retrievable. For every single property, we added all of these attributes. Some things we want to be able to search, some things is just metadata, no search allowed on download count, for example, but we still want to retrieve the value, and so on. One thing that you can also provide, for those of you who have ever used Lucene or Elasticsearch or even Azure Search, is specify an analyzer. So by default, what will happen is when you index anything into Azure Search or Lucene even, by default, there will be certain characters that it will use to break down your string. So if you have a namespace saying newtonsoft.json.jobject, that thing will be broken down to newtonsoft.json.jobject without the dots in between. Because the analyzer doesn't care about the dots, for searching the dots may not matter. But in this case, because we want to be able to search on an actual type name where the dots do matter, we want to say that the analyzer we want to use is the simple one, which is a built-in one that just takes the actual string instead of simplifying it and stripping out the stuff that we don't need. Right, once we have that, we can start the actual indexing. So again, we get the queue pushing input into our function, and then we have to create our package documents. Like I said, lots of code, but you see here that we again download the package that we want to work with, copy it to disk. We create a temporary file stream on disk. Again, NuGet packages can be several hundred megabytes in size. So the last thing we want to do is load them all in memory in our function. It's a function, we don't really have to care about the server, but we do care about the server because we don't want to run or have to run on 64 gigabytes of memory, for example. So we want to store it on the disk of our serverless and then load the package using a package archive reader, basically opening up the zip file, going through all the metadata and collecting title, authors, tags, icon, URL, etc. And then at some point we will open up the assembly stream, use that PE reader, and then go through those type definitions and basically create an entry for our index that we can later on search through. Now, one thing that I do want to mention in here, I know it's lots of code, but it's basically just infrastructure code to open up the package. But one thing I want to mention is that for our index documents, we are adding all of the type names that are in a certain package into one collection in our package document. So if you look at the documents that we put in search, there is a hash set of type names that we populate. By default, if any one of you has ever used Lucene, for example, you will never be able to search in a collection inside a document. Azure Search makes it possible to create collection types inside of an index document, so I can search for a sub-entry of my document here, which is kind of interesting for this use case. Because otherwise, if I would not be able to do this, I would probably have to create a document for every single type in my package instead of one per package, which would complicate certain things. Right, so once we have that, we have the index built and our indexing can continue. Now again, I mentioned, well, the actual indexing takes place up here somewhere. Yes. So the actual indexing, what it will do is create a new index batch, then add all of the documents to my index, catch exceptions, create the index if needed, and so on. So again, you kind of feel that all of this code should not be necessary. We already learned that each function should only be doing one thing well. So in this case, we shouldn't really care about making all of the infrastructure with Azure Search work. Instead, what would be nice is that we had an output binding towards Azure Search. And again, that doesn't exist in Azure Functions, so we will have to create one. So what we want to have is a package indexer with a custom binding where we say we have a document add collector that collects all the documents that we want to store in the index, and then create an Azure Search index binding linked to a certain search service, a certain search service API key, and so on, and then store it into that index. This binding, again, we will have to create, so let's quickly run through it because we've already seen how trigger bindings work, but I'll still cover the differences with trigger bindings there. So again, we have an attribute specifying all of the arguments that we need to work with the search service that we have. Again, we decorate that with binding, and again, I always forget the type names. Again, we will need a config provider. In this case, that config provider, again, is registered as an extension called Azure Search. And in our startup, we also have to register that extension as being an extension. So that's the boilerplate of adding a custom binding. Now, this binding will not be a trigger binding. It will be an output binding. So what we are going to say is, hey, functions extension context, add me a binding rule for the Azure Search Index attribute. Whenever you see this, I want you to know that you should bind it to a collector of open type and a collector called Azure Search Async Collector Builder. What is this open type? Well, I thought when I create an Azure Search output binding for Azure Functions, maybe not everything that I will index throughout my life in Azure Functions will be a package document. Maybe I want to reuse this later on with different shapes of documents that I want to store in Azure Search. How can I make this more generic and make it store any type of document instead of just the one for this use case? Well, that is by using OpenType. OpenType is basically telling the runtime, look, I don't have any type information later, but whatever you give me, I will try to handle it later on. So this will work for package documents that we are trying to index, but also for any other different type that you may want to push into Azure Search later on. The only thing we have to do to map that open type to a concrete type is create a collector builder. And that thing is ridiculously easy. What it does is convert an Azure Search index attribute to an actual typed version. And what we do is basically use the actual attributes that we get in there. Azure Functions already gives me the correct type parameter, so I can simply forward it and this binding will now start working. My collector itself is kind of easy. What it does is, again, give the shape of the document that I want to store. In this case, I will give it to this binding, so that's where the open type comes in, so I don't have the boilerplate of specifying this properties there with this type and so on. That's what the functions runtime will do for me in this case. What I will do, though, is implement the add async methods. Every collector, whenever you want to have something that you can, where is it again? Whenever you want to have a parameter that takes a collector of any type you want to put in there, you have to implement this add async method. So what we do in here is index our item in search service, but we do that in a try catch because when the index does not exist or when the index was not found, then we want to create the index and retry the index operation here. You can add retry logic, you can add whatever logic in here, but again, we previously had all of this logic inside of our function. Now we move it in here and it will be more generic for later usages that we have in any use case that we want to implement. Right, so that's pretty much it. You don't have to build this, but it's kind of nice to have that programming model and simplify all of the infrastructure code in your functions that you have. Right, so we did that. Now we're almost there, and we're almost there in time as well. I see you looking nervously at your watch. I have this, I can do this. The last thing we want to do is build the API that searches in Azure Search and works with Resharper. And in fact, you already saw it in action. I already showed you that I can search for JObject and get that data back. And and that I can, for example, write something that says var foo equals new j, let's say j object, and then do an alt enter and find this type on NuGet. This is actually hitting the index that I created using search. So the API already works and we can already make use of this thing. Now, what does the API look like? Nothing too fancy. It's a very simple API, and that API is implemented as a function as well using an HTTP trigger binding. So whenever a HTTP request message comes in, and I really stress this as an HTTP request message coming in, because functions, the HTTP trigger looks like it's an API to the outside, but it really is accepting messages from the outside. So that's an important thing. Functions is not a hosting platform, it is a hosted orchestrator, and it suddenly handles HTTP messages coming in as well. HTTP triggers you can expose to the internet, and they can have APIs that you can provide arguments to and so on, but let's just dive in and see what this one looks like. Right, wrong one, this one. Okay, so our API, what it looks like is this. We have a find type API, and that find type API has two functions, the find type API and the find namespace API. Why? Because we are able to search for namespaces and for types using two different APIs, so I implemented that here. Is the logic very different? Actually, it's not, so that's why I basically made two functions that under the hood run the same code base. It's just two APIs for a different purpose. What this one will do is build the search texts. Now, I mentioned that we can search in collections inside of Azure Search, and that's what I'm doing here. If I provide a certain type name to search for, what I will say is search the type names column for whatever inputs that I want you to search for. Now, since we use that simple analyzer that keeps track of the dots in the type names and so on, we can search for type names by saying search for dot type name, because that will always be the last part of the string that we push in there. If we search for a namespace, we can do the opposite, search for the namespace followed by a dot, because there's probably going to be types in there as well. So we can kind of influence what we search for here. We then run that against search. For Azure Search, when you search, you can specify a filter as well. We want to be able to show listed and unlisted packages from NuGet. So you can have packages that you can only restore but not search for. We want to be able to provide that filter as well, so implemented that here. And based on whether you allow pre-releases, we also include those in the results or not. We order packages by the search score, descending, and then by the package version, descending. And we run using query type full, which is basically telling Azure Search to not do any magic to the query. We know what we are searching for. This is the data, just handle it and give it back. And then what we do is build the result set, nothing too fancy, just some HTTP going on and some JSON being returned. What does the API look like? Well, if you call it in a browser and you search, for example, for JSON convert or JObjects, you will see in the API that we get back a collection of packages with all of the metadata that we want, all of the assemblies that are contained in there, as well as the type name that we were searching for. So we see we search for JObjects, it's in this namespace, and it's a type, which is the 0 in this case. And that works. We get that data and we can use it in Resharper, as you've seen, to search for certain objects. So we're done, right? Well, actually, we are almost done. There's one thing missing, which is download counts, and I already kind of mentioned this. The v3 API of NuGet doesn't expose download counts. If you want to help me out, find this issue, take a picture, go to that issue and upvote it. So nudge them to expose this API. I'm using my powers of being a speaker here. Now, when that data eventually comes around and when that data is exposed in the NuGet API, what we want to do is update our search at some point. Now, the last thing we want to do is have to reindex every single time we get new download counts. So what we want to do is update existing documents in Azure Search. And it's not in the code because I don't have the data, but what you can do is upserts into or merge inserts into Azure Search. So basically what you can do is use that key field that we added to the package document and simply give it the key plus the new download count, and it will update that single value in search without me having to reindex everything that is in there. Right, we're done. We have everything we have. We have a function collecting changes from the NuGet catalog using a custom trigger binding. We are downloading binaries. We are indexing binaries using whatever is in the NuGet package, and we have it available in an API. We used custom bindings for that trigger to have the separation of concerns and have each function only do one thing and only do one thing well. And yeah, that works. How much time do I have left? Oh, I thought you were going to interrupt me.
I caught you with the functions logo right in your forehead.
Yes. Right. All of our functions can also scale independently. So we have the indexer, of course, or the collector. That's only one instance because we have this cursor on the catalog. That's only one instance. But everything that is queue-based here, we can run multiple of those and index on multiple machines and multiple function instances. The last full index we did back in May ran in 12 hours on 2 B1 instances. For those of you who know VM sizes by heart, that's not a big, powerful machine. That's even a shared core, low memory, stupid kind of machine. And it's really fast to run using this approach. I think if we scale it up to a machine with a little bit more memory that can run a little bit more things in parallel, we can probably index it much faster than 12 hours. But to contrast, the current one that we have that runs on OData takes 2 weeks to index things. So 12 hours is pretty okay, I think. We found that the NuGet.org homepage, at least back in May, listed 1.7 million packages. We found 2.1 million. So I have no idea what is wrong there, but they should update that count, I think. We also found 8,400 catalog pages, good for about 4.2 million catalog leaves, which is roughly the double of those 2.1 million packages that you see there. So I mentioned that NuGet did some package signing over the new year this year, and that's basically every entry that was there doubled because the package signing happened in that catalog as well. So that's very, very visible in the data. Some closing thoughts, and then I promise I will leave the stage. I just created a couple of functions all in one project, all running in the same namespace and so on. What I would probably do if this goes to production is put every single task of my functions in a separate function app. Why? Because first of all, I don't want the fact that my indexer is going berserk. I don't want that to influence my search API, which is the thing that the end users are using. So what I would want to have is that the HTTP APIs are in a separate Azure Function app so that those things are not broken when something else breaks down. Also in terms of scaling, maybe if we all of a sudden get lots of users making use of this feature in Resharper and Writer, maybe you want to be able to scale up the number of HTTP processors in that function or the number of HTTP trigger instances in there, but not necessarily the indexer because NuGet packages keep coming in at the same pace anyway. So I want to be able to separate those in terms of scaling, but also in terms of fault domains. If something fails, we want to make sure that the thing will keep running. Those bindings, I have mixed feelings about them. First of all, I love them because they really take out all of the boilerplate infrastructure code out of your functions and are hosted separately. The downside is that they are specific to Azure Functions and Azure Web Jobs, do not forget. Which means that I'm kind of bound to that platform if I want to do these things. Now, the good thing is usually a binding that you create will be something that handles I/O or interfaces with another system. So probably even if you would go to AWS or want to run on OpenFaaS or build your own container orchestrator and functions orchestrator, you can probably replace those with anything else. If framework lock-in matters to you, maybe you don't want to use too many of those custom bindings. If it doesn't, go wild with them because I think they are really awesome and make the code much more readable, much more reproducible, and so much easier to spike some new ideas there. With that, thank you for being here and enjoy the last session after me. Thanks.
All right.